I'm Kyla Drury.
I'm Hope Diamond.
I'm Thomas Maceda.
And I'm Chandan Bhandari.
And we're the Condensate Collection and Treatment Team. Our team is a combination of the environmental and mechanical engineering departments at UConn.
Pfizer facility in Gran uses 225 million gallons of water per year, which puts it as the top consumer globally in the portfolio of Pfizer facilities. Right now, there are 22 air handling units that are collecting the condensate and draining it in the sewer, as you can see it in the picture on the right. Our job is to design a system to collect the condensate and treat it and send it in the cooling towers, as you can see it on in the picture on the left.
The scope of services we will be providing to our client include calculating how much condensate is being produced, testing and treating the condensate, and transporting the condensate to the cooling tower for reuse.
We extracted climate data from NASA Power and used a mass rate balance to calculate condensate flow rate. The design that includes the air handling units on the first floor has a potential to save 3.25 million gallons of water per year with a maximum flow rate of 71 gallons per minute. The design that only uses the fourth floor air handling units is projected to save about 1.38 million gallons with an average flow rate of 45 gallons per minute. The chart on the right demonstrates the average amount of condensate per year for both designs.
There are four main parameters that we have to treat for on the environmental side. These include pH, Legionella bacteria, which will be treated through disinfection, total suspended solids, and the final parameter is hardness.
On this slide, we have a CAD model and a short animation that demonstrates how the design is laid out in the facility. The condensate starts at the air handling units. It is drained into the mechanical room where it is treated and then pumped through the parking garage to the cooling tower. In the mechanical room, there is a series of equipment used in this project. It starts with the condensate entering a tank. Once the tank is full, a float switch will start a pump, which transports the condensate through a filtration and a disinfection system. After this, the condensate travels to the cooling tower. To the right is a CAD model of the mechanical room. As you can see, the condensate enters to the right. We have a shutoff valve at this point so the system can be shut down during the winter months to prevent freezing. The condensate then moves through the rest of the system and is transported out of the mechanical room.
We specified the filter based on the flow rate, the pressure loss, as well as the amount of TSS, and these were the options. The one chosen is the one on the far left.
The next step in the treatment process is to treat pH and hardness. Because the two impact one another, when raising hardness, pH also changes. We're going to need to first increase the hardness using calcium chloride on the left there, and then add acid to combat the raise in pH and bring it into the range of 7.25. So we'll do that with the addition of sulfuric acid, which is shown on the right. The final step in the treatment process is UV disinfection. For this part, we're going to use the Trojan UV Fit, which is a similar design to that in the UConn reuse plant, and it's designed to remove any Legionella from the water at the required dosages. For our alternative design, we will not be including the air handling units in the basement. So because of this, it's going to be a gravity-fed system with no tank or pump required. We're going to have less condensate, so the flow rate is going to be reduced to about 45 gallons per minute. And with this, we're going to have revised treatment system that's scaled down to handle lower condensate flow rates. Ultimately, Pfizer wants to ensure that this project is going to be financially feasible. Although the environmental benefits of saving water is a really positive thing, if they aren't going to be saving money, it's not a good option. So our first design, including the basement air handling units, is going to produce savings of $16,600 per year on water. and is going to cost about $126,000 to implement the design. So they're going to see a return on their investment in about 8 years. And for option 2, which only includes half of the air handling units, the savings in water are going to decrease to about $7,500 per year, but design and labor also drops to about $69,000 per year. And with that design, they'll have a return on their investment in about 9 years. Thank you.